Well, welcome everyone. And like Blaine said, I work in the Physics and Astronomy Department at ETSU. All of these fossils in life would never have gotten going if it wasn't for the sun. The sun is the main driving force of our solar system. Every piece of energy we use on the planet got its start from the sun. So it's important to understand where the sun came from, where the planets came from, and about stellar evolution. So, first of all, the solar system and the sun were formed about 4.6 billion years ago. The reason why we know that, first of all, deals with one of the best age daters we have, and that's radioactive dating. When radioactive elements decay, they follow a certain curve called an exponential decay. And there's a variety of different elements that are used to try to estimate the age of rocks and other things. Probably have all heard about carbon dating. Carbon-14's half-life is really short. It's only 10,000 years or so. So as a result, you can date things that were living in a recent past, but you can't use it to date really old rocks. But you got potassium-40, which decays down to argon-40, and about half of it will decay in 1.3 billion years. Rubidium-87 will decay down to strontium-87, and half of that will decay in about 47 billion years. Quite a long time. Uranium-235 down to lead-207. It takes about 0.7. And one of the best is uranium-238, which about half of it will decay down to lead-206 in about 4.5 billion years old. Now, the age of the Earth and the meteorites, the Earth rocks, the oldest ones that we find, are on the order of about 3.8 billion years old. Moon rocks are quite a bit older, 4.2 billion years old. But meteorites, these are the stuff from which the planets were made out of. They're 4.6 billion years old, so that's how we know that the planets in the solar system got its start at around that time. Now, from what we understand of stellar evolution, and we do understand stellar evolution very well, with the sun's current temperature and luminosity, it's about a 4.5 to 5 billion year old star. So as a result, everything is consistent in terms of this date for the sun and the solar system. Now, when stars form, they form out of these big, giant gas clouds called giant molecular clouds. The nearest giant molecular cloud to our solar system is off in the direction of the constellation of Orion and Taurus. As a matter of fact, that's why you see so many bright stars off in that direction. They're young, hot stars that are just really coming online over the past few billion years. Well, when stars form, something's got to cause it to collapse down to a smaller thing to initiate thermonuclear reactions. As that happens, though, you get disks that form around stars, and in these disks, you get some very interesting processes that go on. Accretion is one of the most important processes that create planets, and here you've got little pieces of dust and dirt that start sticking together. Some of it breaks apart, but others stick together and start building bigger and bigger pieces. And then you keep on going along, and you start to build things that start to resemble things the size of planets, and these are called protoplanets. Now, the process of accretion is actually still going on, although the rate of accretion is not nearly what it was 4.5 to 4 billion years ago. But just back in the 1990s, there was the famous Shoemaker-Levy comet that hit the planet Jupiter, and also we see evidence for impacts on the moon when we see craters on the moon. But here's an artist's rendition of the comet Shoemaker-Levy impact on Jupiter. Now, when the proto-Earth formed, it was very, very hot because it's got all these pieces of material coming in. That kinetic energy gets converted into heat. So because of this, the rock is all molten. Now, when you have molten rock, heavy stuff sinks to the bottom, light stuff rises to the top. So the heavier, relatively common elements, like nickel and iron, sunk to the bottom, most of it anyway, some of it remained up at the top. and the lighter things like carbon, oxygen, nitrogen sort of surfaced up towards the surface. Well, as time went on and the accretion started to diminish, the Earth and the inner planets could start to cool off just through radiation leaving the surface of the planets. Now, when this happened, we got a solid crust that formed, but there were a variety of outgassings going on because the interior was still hot. And these outgassings then would produce a primitive atmosphere. And the Earth's original atmosphere was composed primarily of molecular hydrogen, carbon dioxide, molecular nitrogen, water vapor, methane, and ammonia. Now, with the Earth, it had a very interesting evolution. But before we talk about that, let's then talk about the rest of the planets in the solar system. There's 4 inner planets, and these are rocky planets. They're called the terrestrial planets. Terrestrial, that's Earth's name, Terra. So terrestrial means Earth-like, small and rocky. And then there are the big gas giants, the so-called Jovian planets. Jovian after the planet Jupiter. And then back when this slide was made, Pluto was still called a planet, but now it's called a dwarf planet. So Pluto is sort of an oddball out there. But there's a variety of other oddballs that have been discovered over the last 10 years out beyond the orbit of Neptune. Now, as I was starting to allude to, the Earth's atmosphere evolved over time. Now, when we look at the planet Mars and the planet Venus, it still primarily has its original atmosphere. In the original atmosphere, you got mostly molecular hydrogen, but because these planets are small, the gravitational fields are relatively weak, and they're close to the sun, hydrogen gas velocity will exceed the escape velocity of the planet and will slowly outgas into the interplanetary disk and out into interstellar space as time goes on. But the heavier molecules like CO2 and N2, those will stick around. And indeed, the planet Mars and planet Venus has primarily a carbon dioxide atmosphere with a bit of molecular nitrogen. Mercury doesn't have any type of atmosphere because it's too close to the sun and too small in order to hang on to any gases. The Earth is different though. The Earth lost its molecular hydrogen and primarily had a carbon dioxide atmosphere like Venus and Mars with 10%, 20% nitrogen and some remnant water vapor, methane, and ammonia. However, Earth was at the right position from the sun that water could condense into a liquid. Now, water has a very interesting property in that it reacts with gaseous carbon dioxide. And the liquid oceans was able to skim out the carbon dioxide from the atmosphere, producing primarily a nitrogen atmosphere. Well, this was good in a way because then it allowed the Earth not only to experience what Venus experienced in terms of a runaway greenhouse effect, but also it allowed life to get started in this liquid oceans. Now, what about the formation of life? Well, there was a very famous experiment done in the 1970s by Miller and his PhD advisor, Harold Urey. It used to be called the Miller-Urey experiment. Nowadays, it just goes by the Miller experiment. But they essentially took compounds that were thought to be relatively common in the early Earth's atmosphere. That is, simple molecules, carbon dioxide, methane, water vapor, etc. And they did 2 different experiments. One where they shined ultraviolet radiation into the container, and another way they introduced electricity representing lightning. And in both cases, they were able to form amino acids, which are organic molecules, the building blocks of life. Proteins are made up of amino acids. So as a result, just quite naturally, at least the building blocks of life could come online pretty straightforward, in a pretty straightforward manner. Now, life on Earth is primarily composed of carbon. And the reason for this is because this carbon can make some really nice long molecule chains because it's got a very strong electronic structure to it to enable to make these long molecule chains. And if you have long molecule chains, you can start to do some pretty interesting things with them over time. And there's a lot of carbon up in the Earth's crust because it's a lighter element and it was able to come up to the top during the differentiation process. Now, as time went on, these carbon atoms, mixing with other type of atoms and molecules, started to rearrange themselves and got into a position where they could start to reproduce themselves. And as time went on, mutations could occur. These mutations could result primarily from cosmic rays, but also from radioactive decay of rocks in the Earth's crust. So both these things could cause mutations. Most of the mutations caused the thing to die away, but some of them were more beneficial, and these things were able to adapt to the environment and then continue to evolve. And this is the whole process behind natural selection. Those entities that are best suited for a given environment, they'll survive, the others will die away. Okay. Well, one question we can ask is, what's the origin of the carbon atoms? And I did already mention why we get these mutations, but essentially, this deals with things that are going on in outer space, essentially dealing with the stars. By the way, here's a picture of an external galaxy, and it's thought the Milky Way galaxy looks something like this. The Milky Way galaxy is our home galaxy. And if this was the Milky Way galaxy, the sun would be somewhere out here, so very far away from the center of the galaxy. Now, one thing astronomers do is they like to catalog things, just like geologists like to catalog things. But back in the early days, astronomers did a lot of that. And there was a very interesting study done by Hertzsprung in Germany and Russell in America, where they plotted the brightness of stars versus their temperatures or their colors. The color of a star is based upon what temperature it is. If it's really hot, it will be bluish. If it's cooler, in the middle part of what's called the main sequence, it will be sort of yellowish like the sun. And then if it's cool, it will be reddish. And here's a little representation of this Hertzsprung-Russell diagram. 90% of the stars that they plotted fall on this sort of S-shaped curve on this diagram here. You got a clump up here, which we refer to as red giants, and then some very luminous guys up at the top, which we call supergiants. And then you have these little strange, hot, very faint objects, which are called white dwarfs. And one question that was asked is, why do the stars pattern themselves in this method on the HR diagram? Well, it results from stellar evolution. It turns out that these group right here, the main sequence, these represent hydrogen core burners. Now, stars, when they're going through the thermonuclear lifetime, thermonuclear means that you're fusing lighter elements into heavier elements. Hydrogen is the easiest element to fuse, and it produces in its end product helium. Well, since the stars started out with primarily hydrogen, and indeed they're still almost primarily hydrogen, this is the first thing to start fusing. And the reason why 90% of the stars fall on this main sequence, these are stars that are burning hydrogen in their core. And because this epoch in stellar evolution lasts about 90% of the thermonuclear life of a star, that's why 90% of the stars reside in that band. Now, as I alluded to earlier, let's talk about how stars are formed. Well, we got these giant molecular clouds. Here's the famous Eagle Nebula in the constellation of Sagittarius. This is the eagle right here, sort of standing on a tree branch, and then another tree branch over here. This is a Hubble Space Telescope image, and this actually has also been labeled the fingers of God, or the fingers of creation. But anyway, you see little pockets here where you got these like reddish objects. These are embedded protostars that are in the process of forming out of stellar collapse. Well, a giant molecular cloud will primarily remain stable unless something steers it up. There are two things that can steer it up. As I showed you in that earlier picture of a spiral galaxy, spiral galaxies, the Milky Way is a spiral galaxy, has these two spiral arms that come out of the center of the galaxy. These arms will rotate as the galaxy rotates. Well, when one of these enhanced density regions smashes into a giant molecular cloud, it can compress the cloud and cause the gravitational field to enhance, hence cause a collapse, which then sets up the star formation. Well, after that happens, stars will collapse based upon what their mass is. The most massive things will collapse relatively quick in just a few million years. Indeed, perhaps a few tens of thousands of years for stars as massive as 100 times the mass of the sun. Big stars will burn their fuel, their hydrogen, then their helium, then their silicon and magnesium, up until they get to iron, in a fairly short period of time, less than, 100 million years or so. When these stars die, and we'll talk about this in a little bit, they explode in supernova explosions. Well, a supernova will then send out a shock wave, and since these things born while they're still in their clouds and explode when they're close to the clouds, they'll then set up further stellar collapse and cause even more star formation to occur. Well, as the giant molecular cloud starts to collapse, it gets smaller and smaller, but as the cloud collapses, it fragments. Now, in the giant molecular cloud, there are these little eddies and turbulences, just like going through a cumulus cloud on Earth. And when you get a cloudlet that sort of separates from the big cloud, it will have a net rotation associated with it, and its density is enhanced, so it will continue to collapse. And as it gets smaller and smaller, it will spin faster and faster and faster, following the law of conservation of angular momentum, which you've all seen if you've ever seen an ice skater go into a twirl. They'll leave their arms out, go slowly, and then bring their arms in and go really fast. Well, that's conservation of angular momentum. And the same thing is happening with the stars. As they get smaller, they spin faster. Well, as they spin faster, the material by their equator starts to get spun out, and the poles collapse in. And what happens is you get a disk that forms around a star as it's forming. And it's in this disk then that planets can form. Well, we call these cloudlets and these protostars, we call these regions in space stellar nurseries. And indeed, the nearest stellar nursery to the solar system is off in the direction of Orion. If you've ever seen the sword of Orion, that center star in the sword is the Great Nebula of Orion. That's a stellar nursery. Stars are being born there right now. Now, as the protostar starts to shine, most of its light's coming out in infrared light due to the collapse. It's not hot enough yet to produce visible light, at least not a lot of visible light. But what happens is that the light pressure starts to get so great that it starts to push on the gas that's collapsing downward, and the star starts to go through a spring cleaning phase and push out all the dust and gas that did not get used to build a star or a planet. And in the spring cleaning phase, which are sometimes called the T Tauri stage, after T Taurus, which is a star in the constellation of Taurus, which is going through this phase right now. But then once that phase stops, the temperatures and pressures at the center of the protostar get high enough for nuclear fusion to occur. Once that happens, it keeps going, and then you have a star that's born. And the system then settles down because there's no more accretion, no more collapse of clouds going on, and a star and solar system will then go off and live its merry life based upon what's going on around it, sometimes quietly, sometimes you might meet some destruction if there's a supernova that goes ignites nearby. Well, let's talk about life on the main sequence. Well, Like I said, 90% of the star's lifetime is on the main sequence. These are hydrogen core burners. Now, what's going on here is that this fusion of hydrogen will produce helium, and over time, the core will get depleted of hydrogen, enhanced in helium. And that will go on and on and on for quite a long time. In the case like the sun, a one solar mass star, it will last 10 billion years on the main sequence. A very massive star, 50 solar masses, might only last a few hundreds of thousands of years on the main sequence. Actually, anyone here familiar with the star Betelgeuse in the constellation of Orion? That's a red supergiant star. That's a massive star. It's 16 solar masses. That's our nearest supernova candidate. And when Betelgeuse goes off, fortunately it's far enough away that it won't hurt life on Earth, but man, that's going to be a brilliant sight. That thing will be brighter than the full moon, but as a point-like object. It will cast shadows on the ground. It will be so bright. Unfortunately, the famous hourglass shape of Orion will disappear after the supernova dissipates, which would be a shame, but during the time of its supernovae, it will look really impressive. Well, once we get a main sequence star, the helium keeps on building up and building up and building up. Hydrogen gets depleted. A time is reached that you have nothing left but helium. Well, it takes a lot more temperature to fuse helium into the next heavier state, which is carbon. Well, what happens then, the core goes out of equilibrium. And see, right, stars in the main sequence, they got a balance between the nuclear pressure due to the heat pushing out and gravity trying to pull the star in. So it stays stable. The sun's relatively stable. But once that fusion stops, the helium core goes out of equilibrium and starts to collapse, getting hotter and hotter and hotter. And that collapse will continue until the temperature gets high enough for helium fusion to begin, and then helium will fuse into carbon and some oxygen as well. Now, when we look at the periodic table, the most abundant elements on the periodic table are hydrogen. In terms of numbers, 9% of all the atoms are hydrogen, 10% or 9% are helium, and everything else is everything else. But other than everything else, oxygen, carbon, and nitrogen are the three most abundant elements after that. And that's because that's the next stage of evolution of these stars as they fuse. Now, when this happens and the helium core ignites, while it was collapsing, it's dumping energy into the outer envelope of the star, and this actually causes the star to start to expand outward. As it expands outward, it cools. So a smaller dwarf star, or main sequence star, will expand up and become a red giant star. In 5 billion years from now, the sun will turn into a red giant star. And that will certainly signify the end of life on Earth. Actually, life on Earth only has about 1 billion years left to go. The sun is very, very slowly, it's not measurable right now, but we know through modeling that the sun is slowly getting brighter. And in about 1 billion years from now, the temperature on Earth will be too hot for liquid water to exist. As a result of that, life won't be able to exist either. So we got about 1 billion years, assuming humans are still around, to get the heck off the planet. Okay. Now, I've already alluded to what goes on next. You get the formation of a red giant star. Then for small mass stars, this helium fusion will take place, producing a carbon-oxygen core. And then when that goes out of equilibrium, when that stops, the helium fusion stops, the carbon-oxygen core goes out of equilibrium and will collapse down. Now for stars about as massive as the sun, the temperature is not going to get high enough in the core for carbon and oxygen to fuse. And as a result, the sun will die as a degenerate object called a white dwarf, and it will be a carbon-oxygen white dwarf. However, more massive stars, they can still fuse to heavier elements. Oh, by the way, When you get this fusion going on of helium producing carbon and oxygen, these stars, red giants, have very deep convection going on. And as a result, it intermixes the enhanced elements down from the center of the star out to the surface of the star. And indeed, I have studied stars called carbon stars, where enough carbon's been brought up to the surface to exceed the abundance of oxygen. Oxygen is typically more abundant than carbon, but in the case of these carbon stars, the carbon will get enhanced and produce a carbon star. Well, not only that, but also you start to produce a stellar wind as you get this final state into a white dwarf, and that will produce a planetary nebula. But this material then goes out into the interstellar medium, which then can be used for future star formation. Hence, the metal abundance. Astronomers call everything heavier than helium a metal. It's not the way engineers and chemists will call metals and metals. Astronomers, everything heavier than helium, we call it a metal. So we talk about the increased metallicity in the galaxy as time goes on. Now, one thing that's of interest is that the sun is relatively old, a relatively old population of one star, and we'll talk about stellar populations in just a little bit. But you gotta have carbon to make life. So as a result of that, you need population 1 stars in order to produce life. So you often hear science fiction stories, people talking about, oh, well, there might be, 10 billion old life forms out there. And that's probably not the case. At least if it is the case, they're not composed of carbon. They're composed of something else. It takes carbon to make life. So we may be the first life forms in the universe, at least in the Milky Way galaxy. So as a result, it could be that we're the first ones to start exploring the Milky Way as time goes on. Well, for the high mass stars, like I said, they can go on to a further type of nuclear fusion in the core to make even heavier and heavier elements. And after you get helium burning the carbon and oxygen will fuse to make neon will fuse to make silicon will fuse to make iron. However, iron is a special atomic nucleus. For really light elements, you get energy out of the nucleus by fusing it. For real heavy elements, you get energy out of the nucleus from breaking it apart. That's the difference between fusion and fission. Iron sits right at the middle of those two extremes. You can't get energy out of iron's nucleus by either fusion or fission. It takes energy to do something with iron after that. It won't release energy. So as a result of that, once you get an iron core that builds up, then once it goes out of equilibrium and starts to collapse, nothing's going to stop its collapse. And it will keep on collapsing down until the electrons that are still in the gas start getting closer and closer together and are forced into the nucleus to interact with protons to produce pure neutrons. Then the neutrons will continue to collapse until they touch each other and can't go any further. When that happens, though, the production of this neutron star, it will happen in a sudden crash and bounce. The bounce sets up an enormous shock wave, which propagates through the material in the outer part of the star, and that's what a supernova explosion is. So as this shock wave goes out of a supernova, it's doing more nuclear enhancement, and things that are heavier than heavier than iron get made in this type of process. So things like uranium and lead and gold and silver, that's all products of supernovas, which is why they're relatively rare, is because they're only made when a star blows up, a very massive star blows up. The most massive of the stars, however, won't stop at a neutron star phase. They'll collapse even further, where the neutrons will collapse under their own weight and keep on going down to a zero volume point in space called the singularity. We call such an object a black hole because there's a region around the singularity where the escape velocity is equal to the speed of light. So anything inside that horizon can never get back to the outside universe because one can't go faster than light. one thing that's of importance of supernovas is that besides doing this extra nuclear processing, it also accelerates material to speeds that's very close to the speed of light, which then gets sent out into the galaxy and perhaps across the entire universe. These things are referred to as cosmic rays. The Earth is continually hit by cosmic rays, and indeed, every so often, some of the more energetic cosmic rays actually make it down to the ground through the atmosphere, and then can cause mutations to occur. Well, let's go through a whole history of the universe. And then I got a few comments about the extinction events, which I'll talk about as well. Well, the universe got started, and actually, when I wrote this, there was a range, but right now we know the universe is 13.7 billion years old. The WMAP mission confirmed that. And at that time, everything in the universe was condensed down to essentially a point in space, representing perhaps a singularity. That then, for some reason, started to expand and went through a very exponential type of growth in a process known as inflation. Well, once that happens, then you start getting a conglomeration of material to form these filaments, which we've seen with the cosmic microwave background explorer in the background radiation of the Big Bang. And then in the places where you got heavy knots, that's where you can start getting star formation to take place. And then once that happens, you just go through stellar evolution to produce all the elements in the universe. So, we start off with pure hydrogen and helium from the Big Bang. By the way, the universe during the Big Bang couldn't make anything past, well, very little past helium, made a little bit of lithium, because as it was expanding, it was cooling. And once the helium fusion ended, the universe was too expanded and too cool for helium fusion to make carbon and oxygen. So everything heavier than helium and lithium had to come from stellar evolution. So when Carl Sagan used to say, "We are star stuff," that was a very valid statement. The stuff we're made of was caused by processes going on in stars, either in low-mass stars slowly burning to make carbon and oxygen, or through supernova explosions to make, they also make carbon and oxygen, but also make all the heavy things in the galaxy. Well, the first stars, these primarily hydrogen and 10% helium stars, these are referred to as population 3 stars. You may wonder, well, why aren't these called population 1 stars instead of first stars? Well, because we're geocentric and solar centric, so as a result, the sun's a population 1 star. The sun is relatively enhanced in metals because it came along some 8 billion years or so after the Big Bang. So there was a lot of stellar evolution that was able to enhance the material that the original solar nebula was composed of. Hence, we have enough material to make us. But as these first stars started to blow themselves up, they started to seed the interstellar medium with heavier elements. And then the next set of stars to get made are called population 2 stars. And these stars have some metallicity, up to about maybe a 10th metallicity of the sun. And then once you get beyond 10th metallicity of the sun, we then call them population 1 stars. So the population 1 stars actually didn't come online until about 7 or 8 billion years after the Big Bang. So the sun's actually a relatively old population 1 star. Now, one thing to mention, I've talked about how stellar evolution impacts life, that is through cosmic rays and through the whole process of making elements in order for life to have material to be made out of. But there are also events in the sky that can end life as well. There's been mass extinctions on the Earth, and indeed the famous dinosaur extinction event is now thought to be due to an asteroid impact that occurred down in Mexico. It could be that some other extinction events also might have had some collision type event to take place. But also there are these things called gamma ray bursters, which are very, very massive stars. When they collapse and explode, they're such an explosion that they produce the highest energy type of photon, a gamma ray. And if a gamma ray burster was to take place near a civilization that had life on the planet, that life would be completely extinguished. Actually, the atmosphere of the planet would be completely ripped away. So fortunately, we don't have any super duper massive stars close to us, so we don't have to worry about gamma ray bursts at all. But there's been other suggestions that have been made as well that might give rise to some of these asteroid impacts and comet impacts. And there's, about, I think it was in the 1980s, somebody put forward the suggestion that maybe there's a very faint red dwarf star or brown dwarf star that's a binary star to the sun. Now the reason for this is that the extinction events seem to occur on a relatively periodic nature. So as a result, well, a periodicity might indicate something in orbit about the sun. Well, it's thought then that this red dwarf or brown dwarf was in a very elliptical orbit, and then when it got to its closest point to the sun, still very, very far away from the sun, 1,000 astronomical units, where an astronomical unit is the distance between the Earth and the sun, it would stir up the Oort cloud of comets. Comets, which is this spherical distribution of ice balls surrounding the sun, would cause these things to come into the inner solar system and perhaps collide with the Earth and cause extinctions. The Nemesis planet, or Nemesis star, as it's been called, is no longer seriously considered because we've had two large infrared space telescopes, the IRAF mission back in the 70s and 80s, and the now current Spitzer telescope. These telescopes would have seen something that close and that cool to the solar system. These infrared telescopes, the far out planets, they're enormously bright in these telescopes. A red dwarf star or a brown dwarf star would be incredibly bright in such a survey of a telescope that is sensitive in infrared wavelengths. So we've dismissed the Nemesis hypothesis for extinctions. There's been another suggestion, though, as well. As the sun goes around the Milky Way galaxy in the disk, it's actually not a flat ellipse or a flat circle that it follows. Because the disk of the Milky Way galaxy has some mass, the sun actually bobs up and down as it goes around the center of the galaxy. And it turns out that this oscillation time period is on the order of the mass extinction events. And it's been thought that, well, gee, maybe when the solar system comes plowing into the disk of the galaxy, it interacts with giant molecular clouds, disrupts the Oort cloud, which then sends comets into the inner solar system. Now there might be something to that. Unfortunately, right now, we're out of phase with this to be a possible type of process that could produce such an event, because right now, we are in the disk of the galaxy. So we'd expect comets to be raining in right now. We don't see any massive influx of comets coming in. So it's probably unlikely that that's the case either. And it could be that there's a variety of combination of things that go on. Asteroid impacts, enormous volcanoes, things of that nature. So it's possible, and perhaps there was a nearby gamma ray burst as well that caused one of the mass extinction events. Who knows? Okay, so anyway, life on Earth wouldn't be here, wouldn't have evolved without the interaction of stars, both to make the elements and to drive mutations and hence natural selection with cosmic rays. So that's my talk. Are there any questions? Excuse me. Yeah.
You're saying that due to models, we were saying the sun's getting in about a billion years, so it's going to be too bright for.
Correct. Yeah.
Is it going to be an increase in brightness so much that no life on the inner planets could be possible, or is it?
What we'll have to do, the best thing to do is have interstellar spacecraft to find a nearby solar-like star. By the way, the increase in luminosity of the sun is not the cause of global warming. It's the sun's light output has been relatively constant since we've been measuring it for 100 years. That's not the cause. It's because we're affecting the environment. That's causing global warming. But anyway, it could be in time that Mars would be well situated for us to jump to Mars. Mars is really small. It's not a big planet. The reason why it doesn't have an atmosphere is there's two reasons. The first one is that it can't gravitationally hang on to much gas. Mars's atmosphere is about 1/100th the density of Earth's at the surface. Secondly, Mars, for some reason, it spins as fast as the Earth, but its magnetic field has stopped. That's actually likely been caused by, because it's a smaller planet, the radioactive decay, which keeps the Earth's interior molten, has died away. There wasn't enough material to keep it molten for this long a time, hence it lost its magnetic field. And then the solar wind pushes on the gas and drives gas off. The primary reason why Mars doesn't have a big atmosphere, though, is because it's a small planet. But could something be done to, I'm not sure we can increase the mass of Mars at all, but certainly we could build domes and stuff like that on Mars. And that's likely going to come far before 1 billion years from now. But certainly you'd want to start thinking about going out of the solar system. Any other questions? Yes, sir.
Lately, we've seen the great meteorological reports about this great storm in the Northeast.
Right.
Are there any scientists working on solar system events from these stars and the waves that are created, the winds, predicting changes in the space atmosphere?
Well, there's no specific models because unless you have data, you really can't constrain a model at all. Certainly people have done a variety of different types of calculations to see what would happen. For instance, as I mentioned about gamma ray burst, if a gamma ray burst went off within a few hundred light years of the solar system, all of the planets, including the big Jovian planets, would have much of their gas completely ripped off due to the increased amount of radiation that's being driven upon them. But in terms of any specific type of models, no, unless you know of an event, you don't have anything to constrain a model in which to do the calculation. And in the case of the Earth's atmosphere, we do modeling based upon zillions and zillions of bits of data from around the world to constrain the models.
So possible journey to Mars, that would not be a consideration, in other words, for a launch out of our atmosphere into predicting a good time to travel?
Well, I mean, we can go to Mars at
You
any
can do
time
it.
now. We can go to Mars now and start building domes. There's nothing to stop, well, politicians can stop bickering, we can do it, but we can do it right now. That's not a problem. It's not beyond our technology to do it. We can't put a big atmosphere around Mars, so the planet just doesn't have the gravitational field to hang on to an atmosphere. So I don't know if any of you saw, I think it's one of the Arnold Schwarzenegger movies, might have been Total Recall, might have been something else, where at the end, there's this, trapped atmosphere in the ice caps or subterranean ice of Mars, and heating it up released all this gas into the atmosphere and made a Earth-like environment. And first of all, you need life to make oxygen in order to breathe, so that's not going to happen. But also, there's not that much ice in Mars, even with the polar ice caps, to produce much of an atmosphere. So you're never going to get a big atmosphere with Mars. It's just not big enough to be on something. Yes?
The original supernova that released in the solar system, did most of that condense into the solar system?
Oh, that's actually something I forgot to mention. I'm glad you brought that up. Actually, there's various tracers of radioactive elements in our solar system that we know had to be produced in a supernova explosion. So it's likely that the sun's creation didn't take place due to a spiral arm coming through, but happened after star formation started, and there was a nearby supernova that exploded, and then caused our local portion of the molecular cloud to start collapsing to make the solar system. So we do know that from, I think it's one of the aluminum isotopes that we know that had to happen.
So it was a cloud of dust and then it got.
Well, the dust, it's primarily gas. There's some dust in the giant molecular clouds, but dust will actually form just as snow will form in a gaseous atmosphere. It just condenses out. And then the dust, dust is sticky. If you ever look under your bed, you see these little dust balls. The same thing happens in space. These things start sticking together through electrostatic processes.
How many cities?
Yeah.
Are the people who study Mars getting any closer to understand what happened to the water on Mars?
Well, it's, back when I was an undergraduate, it was thought the polar ice caps of Mars were completely carbon dioxide. Now we know there's a substantial amount of water in them as well. And certainly looks to be evidence now from the orbiting spacecraft that there are occasional water flow on Mars that happen within, a few thousand years or so. So as a result, it's possible that Mars might have still some water. There's not a lot of water in Mars, so there certainly hasn't been any evidence of large amounts of water. Certainly enough to support the colony for a while, but not enough to support an entire civilization.
Do we know if the giant gas planets in our solar system are constant in size, or are they decreasing?
Jupiter got a little bit bigger when Shoemaker-Levy smashed into it. Actually, there's been a few more comet collisions with Jupiter since that time. They haven't made the press the way Shoemaker-Levy did, but Jupiter is always getting a little bit bigger because it's always gobbling things up. As a matter of fact, we're very lucky that we have Jupiter. Earth would have been plummeted by asteroids and comets a lot more than it has, but Jupiter either gobbles them up or kicks them out of the solar system, one or the other. So we owe a lot to Jupiter as well. And it could be that if you want to start talking about life elsewhere, you want to find, first of all, a planet that has a big moon. The moon actually has a big impact too on life on the planet. It could be that tides raised by the moon brought this organic material from the oceans onto clay and beaches that allow the setup for these long carbon molecule chains to start forming. So it could be, we might be directly a byproduct of the moon's impact in terms of raising tides on the Earth. But also you want to look for a planet that's got a Jupiter-sized thing out 4 or 5 AU from its star to protect inner planets from bombardment. Yeah?
Could you go into a little more detail about how stars would influence evolution and mutations?
Well, essentially it's the cosmic rays. You need the stars to make the elements in which life got started from, and then you need cosmic rays to drive mutations. And those mutations that are beneficial to the environment, they'll survive and multiply. Those that aren't, won't. And more times than not, mutations will lead to cancer and stuff like that, not to enhancements in life. So mutations are destructive more than they're constructive, but for the things that are constructed and can survive, those go on.
Have you figured out a percentage or, like where mutations, like how much of mutations would be of cosmic?
Well, I mean, besides the cosmic rays, there's also the radioactive decay on the planet, and that probably had a larger impact than the cosmic rays did. In terms of people coming down with specific numbers, no. Not that I'm aware of. Yes?
The stars that are being reported in stellar nurseries right now, are they still considered population 1 stars?
Yep. They're even more population 1 than we are.
So there's nothing big.
Yeah, no. Like I said, the sun's an old population stuff of 1 star, sometimes referred to as the disk population. But no, the stars being born Orion right now They're much more enhanced in metals than we are, because there's been 5 billion years of stellar evolution to help seed the galaxy. Yes?
Are black holes stable, or can they become unstable?
Well, that's an interesting question. There's certainly the physics of the evaporation of black holes is a bit too much for me, but Stephen Hawking has done a lot of work to show that very small mini black holes will evaporate over time and perhaps completely disintegrate. Large black holes, can they evaporate? Well, they can, and the process for this is that if you got this event horizon, if you're talking about a stable, non-rotating black hole, then those black holes really can't lose mass. However, a black hole that's rotating, certainly all of them are probably rotating very fast. You get different regions in the event horizon. There's this, I forget the name of there's some name for a region sort of in between the event horizon and another horizon of some type of a rotating black hole, that you can get material to go in and then pick up energy, then leave, and then sort of take energy away from the black hole. Energy is mass, E equals mc squared, so a black hole loses mass as a result of that. Also, if you get a what's called a virtual particle, which can form in very intense gravitational fields, and that makes a matter-antimatter pair, which then quickly hits each other and annihilates the photons again. However, if you get one of these virtual particles that form right at the event horizon, you might get the antimatter particle going across the event horizon. The other one doesn't. And as a result of that, then the black hole loses a little bit of mass from its energy field. That's another way for a black hole to lose mass. It's not a very efficient mechanism, however. So it's unlikely that stellar mass or big or supermassive black holes are likely to completely evaporate away. It's the mini black holes that Hawking has suggested that should be the ones created at the Big Bang, should be evaporating about now. We haven't detected any mini black holes evaporating. It should be a big gamma ray event when that happens, but we've seen these gamma ray bursts, but we know what those are. They're not mini black holes going on. So there's no, right now it looks like Hawking's idea isn't going to bear fruit at all. It's an interesting idea, but it looks like the data's not there. And of course, science is data driven. Anything else? Well, thanks for the great questions. I appreciate it.
So.